Hey everybody, how y'all doing out there? I'm doing good. I just had my school's official spring break, so that was kind of nice to take a week off and take a breather and re-catch up with everything. I'm wondering if some of you guys were on spring break, if you call, I mean, this is kind of spring break for everyone right now, a little bit, but also not. I know it's crazy. So kind of while we're waiting for people to log on and get ready, I'm curious as to what you've been cooking. So what kind of food have you been cooking? For me, let's see here. I made carrot cake the other day. So what food are you cooking? And cauliflower pizza. Nice. Hello. Once again, what food are you cooking? Just out of curiosity. My poor partner had her birthday, and I had to I had to make her a carrot cake. We made it together. It was actually quite fun, but she didn't have to get a have like a fancy dinner or anything like that. So I made carrot cake. But yeah, nice. Cauliflower pizza is really good. Was now the question, Perla, I have is: was the cauliflower on the pizza, or was the dough made of cauliflower? Rita toast. The dough. Yeah, that's awesome. I've totally had that before. That sounds really good. Awesome. So, just kind of remind everybody a few things. First off, over on the right hand side, we have the chat. You can right now list the foods that you've been making. Other than that, though, if you guys have any chemistry related questions or statements that you want to put in there, please go ahead and do that. There's also down below a ask a question tab where you can ask a question specifically there. And then at the bottom, I've also listed my slides, which I'll be doing and using today. So if at any point, those are pretty much the main three things that you need to be using. I'll be kind of referencing chat a little bit today. My goal is to kind of go through my lecture and then come back. So I won't always respond to something instantaneously. But if I skip over a question or forget to ask it, feel free to type it in again. I promise I'll try to get to those kinds of things. Cool. So without further ado, why don't we go ahead and get started here? Today, we're going to be looking at specifically the third unit of chemistry, which is intermolecular forces. Now, this is a massive unit. So I do want to give everyone a heads up. We are splitting it into two. Today, we're going to be looking at the main three states of matter, so solids, liquids, and gases, focusing heavily on the gases today, and also what intermolecular forces are. And then in my next stream, which will be next Tuesday, we're going to be looking at the second half of intermolecular forces unit, which will be solutions, Beer's law and the applications of that, and also a little bit of light stuff, which the College Board throws into this unit. It could be applicable to this. It could also be applicable to the photoelectron spectroscopy, which we did at the beginning. So make sure you check out some of those slides and stuff like that. And next week, Perla, is when we'll be starting the twice a week. So today is my last Tuesday only session, and then next week it will be on Tuesdays and Thursdays, 5 p.m. Pacific time, because I'm over here in Santa Cruz. Awesome. So without further ado, here are the other sessions that we're going to be doing as the CRAM sessions. So once again, April 14th, we're going to be doing the second half of intermolecular forces. On the 21st, we're going to be looking at chemical reactions, stoichiometry, stuff like that. And April 24th, which will be 2 weeks from today, we'll be looking at kinetics. I don't think that date is right because today is the 14th. I'm off by a week, aren't I? I'll fix those dates and I'll make sure to put those in there. So next week is April 21st. That will be intermolecular forces part 2. April 24th will be chemical reactions, and that will be April 28th. Yeah, April 28th will be the kinetics. Sorry about that. I'll make sure to upload and fix those slides for you guys later. As always, though, make sure to check out all of our social media sites for information on when those slides will actually be, when those CRAM sessions will actually be. So today, what are we going to be looking at? Today, we're going to be looking at specifically what the intermolecular forces are. We're going to be doing a quick little stint on liquids, a quick little stint on solids, just kind of describing what they are and how particles move within those situations, and then a bigger chunk on gases. I also think that today is going to be a fairly quick-ish CRAM session. So if you guys have any questions at the end, I'll be able to stay around for a little bit. So with that being said, I do want to review. I gave you guys a little bit of a homework assignment last week, and I wanted you to draw a couple of appropriate Lewis structures for the polyatomic ion chlorite. And so this is my first switch around here. I'm gonna go to my whiteboard app here. And this is what I have shown for you guys. I'm gonna go ahead and focus the screen a little bit. This was the Lewis structure that I had provided for you. This Lewis structure here, blah, 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 follows the octet rule. So chlorite is ClO2 1 minus, and once again, it follows the octet rule. So if we were to do the formal charges for the oxygens, just to kind of see how this looks for the formal charge count, the formal charge would be 6 valence electrons on oxygen, minus the dots minus lines. So there's 6 dots around oxygen and 1 line. So the formal charge for each oxygen right now is -1. So I'll go ahead and change the colors for this. It'll be -1 for you and -1 for you. And the formal charge for chlorine will be 7 minus dots, which would be 4 dots, minus 2 lines, which would be a +1. So first off, are our formal charges appropriate? And they absolutely are appropriate. And the reason they are appropriate is because they add up. So -1 plus 1 minus 1 is equal to -1, which is the charge of the molecule. So they are appropriate. That is our requirement of molecule. And then the next question we ask is, do we minimize the formal charge on all of the individual atoms or elements? And the answer to that is unfortunately no. And the reason this is because more than one, actually all of the elements on my polyatomic ion do not have a formal charge of 0. Remember, my goal is to have a formal charge of 0 on some, if not all, of the atoms in the polyatomic ion. So the way I'm going to go ahead and do this is the following. I always remove a lone pair from an exterior atom and shift it to form a bond with the central atom. The way I'm going to do this is by erasing, once again, a lone pair on the one of the oxygens. So I erased 2 electrons, and I move those electrons in. And form a double bond here. So once again, those electrons were here, and I moved them in. So while this doesn't satisfy or follow the octet rule, what is interesting or cool about this now is that the formal charges have changed. So I'm going to go ahead and erase all of this here. The formal charge for this oxygen at the end still will be -1. The formal charge for the oxygen on the right side still will be -1 because nothing changed about that. But the formal charge for the oxygen on the left and the chlorine in the middle have changed. I'm going to go ahead and erase one last thing here. I'm going to erase this count here. So let's go ahead and do that new math. The new math becomes, for chlorine, it has 7 valence electrons. There are 4 dots, and there are now 3 lines. So 7 minus 7 ends up being 0. The formal charge for the chlorine in the middle is now 0. The oxygen on the right, on the left, so formal charge for oxygen, and I'll indicate this with the left, this one is the one on the right, is going to be 6 minus 4 dots minus 2 lines, and it's also 0. So what's nice about this is that the molecule, the way that I've drawn it now, better represents how the molecule looks in terms of formal charge. Now, you have to remember that Lewis structures are models. We're trying to best represent these as best as we can. And we don't 100% know exactly what this looks like. So you just kind of have to follow the language of the question in order to kind of answer it in the way that they want. So if they ever use the words formal charge, know that they want you to minimize those charges. And the way you do that is by removing electrons from the exterior atoms and then moving them in. All right. Yeah, and so Aparna, you asked if there are too many electrons on the central atom, and the answer to that is kind of. Remember, because chlorine is in the third period, like Mackenzie said, it can have an expanded octet. It can have more than 8 valence electrons. All right, cool. So that's pretty much it. That was the review, your homework assignment, and now we're officially going to go ahead and get into intermolecular forces. So let's go ahead and do that. Interestingly enough, last little piece I want to point out, the shape, the bond angle, and the hybridization is still the same after you change or make the resonance structure. So that's a good thing to kind of keep on the back of your mind. All right, so intermolecular forces, which I'm going to abbreviate as IMF. So first off, remember the word molecule refers to a covalent compound. So when we're looking at specifically intermolecular forces, and the 3 intermolecular forces are hydrogen bonds, dipole-dipole, or London dispersion forces, those are forces of attraction felt between covalent compounds. They are the attractive force between molecules. We use IMFs to identify bulk scale properties in compounds. And what we're going to be doing is looking at boiling point, melting point, viscosity, and vapor pressure to help us identify whether or not these molecules have ability to flow around each other, or if they're like really rigid and not moving. So strong intermolecular forces means the following things. First off, a strong intermolecular force means that you have higher boiling points. A boiling point, remember, is defined as the temperature where the vapor pressure is equal to the atmospheric pressure. Now, in the back of your mind, when you're looking at boiling point, you should absolutely think of it as the temperature at which the liquid turns into the gas. That's perfectly okay. The fancy definition, though, is the temperature where the vapor pressure is equal to the atmospheric pressure. And I'll talk about this a little bit more later on today. Strong intermolecular forces means higher melting points. This is the temperature where a solid turns into a liquid under 1 atmosphere conditions. Now, I do want to remind you once again that this is just the temperature where some solid turns into a liquid or liquid to solid. Strong intermolecular forces means higher viscosity. Remember, viscosity refers to the resistance to flow. Things that are very viscous move very slowly. They flow very slowly. Things like maple syrup and honey are very viscous, and that means that they have strong intermolecular forces between particles. And last but not least, strong intermolecular forces means lower vapor pressure. So that's the only one that isn't directly related with the strength of the intermolecular force. Vapor pressure, refers to the pressure of a gas that is at equilibrium with its liquid phase. This one kind of makes sense, mostly because if you have strong intermolecular forces, the particles don't want to escape or exit into the gas phase. They want to be right next to their respective partners. They're very attracted to their partners. And with less gas particles in the gas phase, the pressure of that gaseous system, is going to be lower. So strong intermolecular forces means lower vapor pressure. So this is how I kind of want you to think about it. First off, excellent joke. This is how I want you to think about it. Particles in a solid substance are quite attracted to each other. They're very attracted to each other, and they don't want to move around. Remember, particles in that solid are rigid. They're vibrating, but they're not they're not flowing past another. They're so attracted to their neighboring partners that they're just kind of sitting where they're at and not moving. And that must mean that they have stronger intermolecular forces. So generally speaking, things that have things that are solid at room temperature have very strong intermolecular forces. A good example for this would be sugar. Sugar is a covalent molecule. It's a large covalent molecule with a lot of hydrogen bonds. The molecules become so attracted to other molecules of sugar that they don't flow past one another. What's cool about sugar, though, is that it does have a relatively low melting point because it is a covalent compound, and you can add just enough energy to the sugar molecules to begin to allow them to flow past one another. What's cool about that, though, is that melted sugar is still very viscous, so that's still another representation on how strong intermolecular forces relates to some of the other bulk scale properties of those molecules. And conversely, gases are pretty much the opposite. If you have a gas at room temperature, that means the particles of those gases are fairly unattracted to each other. One gas particle comes into contact with another gas particle and pretty much hits it and collides off. They have to have very, 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 very low temperatures in order for them to condense and possibly even solidify. That must mean that substances that are gases at room temperature have low or very little intermolecular forces. Some examples of this would be like carbon dioxide, oxygen, or nitrogen gases, diatomic molecules. Most of them are gases at room temperature. And once again, that makes sense because particles of gases are not quite attracted to each other. So hopefully at this point in the game, you guys are all fairly comfortable and quick with recognizing the different types of intermolecular forces. They are listed here. These are the main three that will come up in terms of, once again, intermolecular forces. They are hydrogen bonding, dipole-dipole forces, and London dispersion forces. Now, the way I listed them is in order of their relative strengths. Hydrogen bonding is the strongest. London dispersion forces is considered the weakest. Once again, though, the word I used was relative, and I'll come back to that in a second. I'm going to start by talking about dipole-dipole forces. Dipole-dipole forces are the attractive force between polar molecules. Now, in our last session, I went ahead and described how to identify if a substance is polar. And if you're having any issues with that, I would recommend going and watching that video. But remember, a polar molecule is going to be something that is unsymmetrical. Unsymmetrical molecules have lone pairs on the central atom or have exterior atoms that are different from each other. Unsymmetrical molecules are polar. Unsymmetrical molecules are generally polar, and therefore they will exhibit dipole-dipole forces between their partners. So once again, a polar molecule has a positive and a negative end. The positive end of one molecule will attract the negative end of another, and that force of attraction is called the dipole-dipole force. The hydrogen bonding is essentially the same thing. Hydrogen bonding is very, very strong dipole-dipole forces. It is specifically defined as the attraction between molecules that have hydrogen bonded to fluorine, oxygen, or nitrogen. There's a stupid mnemonic that I came up with, me personally. No, I didn't, but I like to say that it. Hydrogen bonding is fun. You have to kind of say it on, not fun, on. Because the only way you can have hydrogen bonding is if it's directly bonded to F, O, or N. You can have a hydrogen with a fluorine in the same molecule. You can have a hydrogen with an oxygen within the same molecule, but if the hydrogen is not directly covalently bonded to one of those three elements, the hydrogen bonding does not exist. Hydrogen bonding is incredibly strong, and there's a few reasons for that. The biggest one being the large electronegativity difference between fluorine and hydrogen. And the second reason is due to the size, the small size of fluorine, oxygen, and nitrogen, and hydrogen. Last but not least, we have London dispersion forces. And once again, these are considered to be the weakest intermolecular force. Yeah, they are also called the van der Waals interactions or van der Waals forces. And this is really just due to the random motion of electrons. Electrons are negatively charged, and if they just so happen to be on one side of the molecule compared to the other, that will make that side of the molecule negative compared to the positive side of the other. Essentially, anything that's a hydrocarbon, the strongest intermolecular force it's going to have is London dispersion forces. And you also want to keep an eye out for those diatomic molecules. The strongest intermolecular forces they feel, once again, is the London dispersion forces. And so Perla asked a really good question in terms of ion dipole forces. Ion dipole forces and ionic bonds I'm going to kind of get to in a second. But just realize those are just other types of interactions. Whenever you add the dash in between two things, it's just describing what two things are interacting with each other. So for example, in an ion dipole force, you're referring to, for example, salt dissolved into water. You're referring to a sodium ion, which is positively charged, interacting with the negative end of a water molecule. So you're interacting with the dipole of water and the ionic charge of the salt. So ion dipole. And that's kind of where that comes from. Ion dipole can have relatively similar strengths to dipole or maybe a little bit above. And then we also have, for example, the other kind of random one that comes up is ion dipole. And not ion dipole, dipole-induced dipole. That's the one I was going to say. And a dipole-induced dipole is when you have a polar molecule interacting with a non-polar molecule, you can actually create or induce a positively or negatively charged and something that normally isn't positively or negatively charged. So I'm going to pause really quick and kind of look at some of the things that are happening in chat. Kate mentioned that her teacher told her there are LDFs in every compound, and that is true. So a question that comes up in the AP is to list all of the intermolecular forces that exist for a molecule. If it says that, the first thing you should put is LDF. Everything has LDFs, and the reason that is because everything has electrons. If London dispersion forces arise due to the random motion of electrons, that means that everything has this intermolecular force called the London dispersion force. It's just that it's not always the strongest intermolecular force. So basically we start there, we say LDFs, and then the next question in the line of logic that you ask is my molecule that I'm looking at polar? If it is, that means that it also has dipole-dipole forces. And then the last question that you ask in terms of that line of logic is there a hydrogen specifically bonded to F, O, or N? And if there is, then you're like, cool, it has hydrogen bonding, dipole-dipole forces, and LDFs. And that's in terms of if they ask you about the intermolecular forces. Ria, you posted something about the LDF should not be used synonymously with the term van der Waals. I would say that, yeah, because the language in terms of the AP has always been the LDFs, the London dispersion forces. And last but not least, could there ever be compounds with only LDF and hydrogen bonds? And the answer is no. And the reason that is because hydrogen bonding is just fancy dipole-dipole forces. Once again, if I were to draw it, it looks exactly the same as a dipole-dipole force. It's just stronger. All right. So moving on, and the last kind of thing that we're going to look at a bunch of things in terms of intermolecular forces, but we should be very aware, very hyper aware of the type of compound that we're looking at. And the reason that is because the type of compound can also help us determine the bulk scale properties. So here's two images that I drew up. The first one is of sodium chloride, and the second one is the intermolecular force that exists between two water molecules. Ionic compounds do not have intermolecular forces. The force of attraction between individual particles specifically is the ionic bond. So the first question really you should ask before any of this is what type of bond exists? Because generally speaking, the attractive force between ions, is a lot stronger than the intermolecular force. And that's why when I'm looking at ionic substances, they have really high melting points. They're considered molten, remember, when they're in the liquid form. Whereas when I'm looking at covalent compounds, all I have to do in order to melt or evaporate a covalent compound is break the intermolecular force. I'm not breaking bonds. So once again, here are the relative strengths of interactions and the main four, in my opinion, that you should be paying attention to. First off, it's hydrogen bonds. Hydrogen bonds are the strongest force of attraction between particles that can move, that can flow. The next is the hydrogen bond. Third is dipole-dipole force. And fourth is the London dispersion force. With that being said, this is just the relative strength. Any of these can kind of flip out of order, and you have to be able to, one, predict, and if you're ever predicting, use this list in this order. The other situation is being asked to explain, and this is a great example. I love the example I'm about to use. So here are two compounds that have fairly different boiling points. So we have carbon tetrachloride, CCl4, which has a boiling point of 76.7 degrees Celsius, and chloromethane, which is CH3Cl, which has a boiling point of negative 24.2 degrees Celsius. I want you to do this first for both of these molecules. I've drawn and given you the Lewis structures. I want you to identify all of the intermolecular forces that exist within these molecules. And then once you've done that, I want you to identify the strongest intermolecular force that exists in both of these molecules. Nice, and Schalke is actually quick on the draw with this. CCl4, the strongest intermolecular force it has is London dispersion forces. It is a symmetrical molecule because the central atom doesn't have any lone pairs on it, and the exterior atoms are all the same. Whereas chloromethane, CH3Cl, is an unsymmetrical molecule, and therefore its strongest intermolecular force would be the dipole-dipole force. Now, if you were to use the list that I provided previously, you would have predicted probably chloromethane to have a higher boiling point. And I probably would have been totally okay with that. Predictions are a good tool for scientists to have, but they don't always work. So the explanation or language that you would use is actually kind of, it looks like what Schalke said. The London dispersion forces are stronger in CCl4 than the dipole-dipole forces are in CH3Cl, and that's perfectly okay. For example, if we were to consider water, water has hydrogen bonding. Water, we know, boils at 100 degrees Celsius. It's a liquid at room temperature. Iodine, I2, is a diatomic molecule, and it's actually solid at room temperature. So the way we would kind of use the language for that would be the London dispersion forces in iodine. The London dispersion forces in iodine are stronger than the hydrogen bonds in water. So just because something, and then this is the last thing, and then I'm gonna kind of move on. Here's the explanation for the people who are looking at it. Anika asks, why doesn't CCl4 have, why isn't CCl4 dipole-dipole? It does have polar bonds, you're totally right. But just because something has polar bonds doesn't necessarily mean the molecule overall is polar. Remember, we have to consider if something is symmetrical or not. And if you need a little bit of help with that, we talked about it in our last unit review, unit CRAM session, so unit 2, I would check that out. But just as a reminder, CCl4 is nonpolar because it's symmetrical. We know it's symmetrical because the central atom does not have lone pairs and the exterior atoms are all the same. And yeah, London dispersion forces can be stronger than hydrogen bonds. Not always. Generally speaking, if you're asked to predict the relative strengths of intermolecular forces, you're asked to compare molecules of the same size or very similar sizes. So yeah, that's something you should kind of keep on the back of your mind. One last thing that I want to point out is biomolecules. So biomolecules is something that the AP College Board could ask about. Biomolecules are essential molecules in living organisms. Essentially, no pun intended on that, all biomolecules are organic compounds. Remember, organic compounds contain carbon. Biomolecules owe a lot of their interesting properties due to hydrogen bonds and other intermolecular forces. And one of the great examples of this is the base pairs in DNA. So what I've drawn on the left is guanine and on the right is cytosine. So the reason that the guanine and cytosine always form a bond in the DNA double helix is because of the way their hydrogen bonds overlap. And you can look up the adenine and thymine. Base pairs and see a very lovely interaction as well. So being able to recognize and name these types of intermolecular forces that exist in biomolecules is super important. Essentially, it's easy to see that these hydrogen bonds exist because hydrogen is directly bonded in both of these molecules to a nitrogen. So hydrogen bonding is bond. Hydrogen bonding is bond. All right, so we're going to quickly glean over liquids and solids just because we kind of have a working definition of these based on our everyday lives. We know what liquids are, we know what solids are. Luckily, there's not a lot of math that's associated with this, and I've already been talking a lot about solids and liquids in my discussion of intermolecular forces. Just a reminder, liquids have a definite shape but an indefinite volume. Particles flow past one another and are still fairly densely packed. Liquids and solids have similar-ish densities. They can differ, but not by very much. There's not a lot of particle difference in terms of solids and liquids. And the one vocab word that's associated with liquids that I wanted to bring up was boiling point again. And this time I'm going to refer to the normal boiling point. The normal boiling point is the boiling point that you will always look up and know. For example, water's normal boiling point is 100 degrees Celsius. Water's normal boiling point is 100 degrees Celsius. What I mean by this is, one, water doesn't always have to boil at 100 degrees Celsius. And two, the state of matter is also dependent on the pressure. Normal boiling point is defined as the temperature at which a substance's vapor pressure is 1 atmosphere. Now, going back to my earlier definition, boiling point is the temperature at which the boiling point is equal to the atmospheric pressure. So if the atmospheric pressure is 1, then you are looking at the normal boiling point. So that's why it changes with elevation. If you were to go higher in elevation, the atmospheric pressure decreases. And since it decreases, that means the boiling point doesn't have to get as, the temperature doesn't have to get as high for the vapor pressure of the substance to equal the atmospheric pressure. Because it doesn't get as high, this is why things take longer to cook at higher elevations. This is a great question. I just kind of threw it in here for you guys to practice a little bit. It says, which of the following particles would have a higher viscosity? Remember, viscosity is a property of liquids. Viscosity, remember, refers to the resistance to flow. What I want for you to do is quickly draw out those Lewis structures and try to identify which type of intermolecular force exists in between these. They're quick, huh? I know, I was thinking the same thing. So I'm going to go over to my whiteboard and quickly draw up these Lewis structures here. So the two drawings we should be looking at are something along the lines of this. We have CH3O, CH3, so H, 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 H. There are 2 lone pairs on the oxygen. And then the other molecule is going to be CH3CO, CH2OH. So it looks like this. I would recommend, if you're not fairly quick with drawing Lewis structures, especially of organic molecules, to practice. One trick that I keep on the back of my mind is that carbon will always have a single bond, carbon will always have 4 bonds, nitrogen will always have 3, oxygen will always have 2, fluorine will always have 1. It's super important for you to be quick with these so you can answer questions that are related to the Lewis structure drawings. Now notice that the molecule on the right has the oxygen and hydrogen directly bonded to each other. While there are hydrogens in the left molecule, and this molecule is called dimethyl ether, none of the hydrogens are directly bonded to the hydrogen in the middle. And because of that, the strongest intermolecular force felt on the left-hand side is a dipole-dipole force, whereas the strongest intermolecular force on the right-hand side is going to be a hydrogen bond. And because of this, the viscosity of the molecule on the right will be greater. The other reason that I can compare these two is because they actually have the same molar mass. Remember, we want to try to use our predictions when molecules have similar to or the same molar mass, and both of these molecules are isomers of each other. So they contain the same number and type of elements, but the molecules are connected in different ways. I'll go ahead and close that. So once again, the question we asked was, which of the following, oops, I want to go ahead and focus the screen over here, there we go, says, which of the following has a higher viscosity, the dimethyl ether, which is CH3OCH3, or CH3CH2OH? And the answer is the first one, the second one. That would be ethanol. The reason that is because it has hydrogen bonding. All right. So moving on. Last thing that we're going to talk about before we jump into gases is the solids. Really, at the end of the day, being comfortable with the fact that a solid structure or substance has the particles in fixed positions. Particles do not flow past one another. They do vibrate and shake a little bit, but once again, they don't flow past one another. Solid substances are defined as having a definite shape and volume. So you can't quite necessarily change the shape of a solid. I mean, you can manipulate the shape, but the shape will not change unless it's manipulated, and the volume is the same. There are 4 main types of solids you guys should keep on the back of your minds. We talked about a lot of these in our last stream. We have ionic solids, which are formed between the interactions of oppositely charged ions. We have covalent network solids, which are essentially giant molecules. If you've ever seen a diamond is actually a single molecule. A diamond is actually a single molecule with carbons bonded to carbons bonded to carbons over and over and over again. Graphite is an allotrope of diamond. Graphite is an allotrope of diamond. Allotropes are basically elements that have different structures. So for example, oxygen gas, O2, and ozone, O3, are allotropes of each other. Next, we have molecular solids. And this is where the intermolecular forces kind of comes into play. So you're going to have a water molecule attracted to another water molecule, attracted to another water molecule. Dry ice is another example of molecular solids. Sugar is also another example of this. And then we also have metallic solids. Everyone, I think, is pretty comfortable with metals. Remember, metals are very good at conducting electricity and heat. Metals are malleable, they're ductile, they're also shiny, they have luster. Some examples of this would be pure gold, so 24 karat gold. Another example of this would be brass, which is an alloy. Brass specifically is a substitutional alloy, and remember, a substitutional alloy is when elements replace other elements in the crystal lattice, in the structure that it is. This arises due to the fact that copper and zinc have similar atomic radii. So boom, that's our intermolecular forces, that's our liquids, and that's our solids on a very qualitative level. I think being able to recognize comfortably the different types of intermolecular forces is really important. And the quickly drawing Lewis structures is also something you should kind of have on the back of your mind. But yeah, I'm going to pause really quickly and kind of see if any questions arise before I jump into gases, which is going to essentially be the second half of our lesson today. So Perla asks, are covalent network solids always the same element? And the answer to that is no. The other example that I gave us are silicates. Silicates are going to be like sand. Sand are types of silicates. And in a silicate, we have silicone and oxygen. And what's happening is the silicone is covalently bonded to an oxygen, which is then bonded to a silicone, then an oxygen, then a silicone, then an oxygen. It just kind of goes on and on and on. It's really cool. They're literally massive molecules. They're gigantic molecules. And because for covalent network solids, in order to melt them, you actually do have to break the chemical bonds that exist between them. So covalent network solids have incredibly high melting points. Yes, Jaina or Yana, these are the only types of solids that are on the AP exam, and pretty much the only types of solids that exist. I mean, you have technically atomic solids, but atomic solids are very similar to molecular solids. And something that's kind of interesting about atomic solids, one of the ones that we would probably look at would be like helium, solid helium. We've actually never turned helium into a solid. It's just we, under our Earth's conditions, under 1 atmosphere pressure, we can't change or manipulate the system in order to turn helium into a solid, which I think is super rad. Nice. So then the last question that I'm going to answer is Perla's question: how are covalent network solids different from molecular solids? And I think that's a really important thing to distinguish or understand. Covalent networks are literally a atom bonded to an atom, bonded to an atom, bonded to an atom, over and over and over, almost infinitely, almost. These are quite literally like, if I were to hold up a diamond, I'd be holding up one molecule where all the things are bonded to themselves. If I were to hold up an ice cube, on the other hand, that ice cube is made up of many moles, or many trillion billions of molecules that are attracted to each other via intermolecular forces. Remember, intermolecular forces are not bonds. And so therefore, the attractive force is slightly different in a covalent network versus a molecular solid, even though both of these tend to be made up of nonmetals bonded to nonmetals. So basically, you have a subunit that's a molecule attracted to another subunit that's a molecule, attracted to another unit that's a another subunit that's a molecule, and the attractive force between molecules is not a bond, it's the intermolecular force. All right, so we're going to move on to gases. As far as gases go, there is something that is incredibly important that I want to make sure you guys are all comfortable with, and that's temperature. I know that seems silly, but there are so many questions that come up with temperature that are so actually straightforward, and you just need to be comfortable with your language behind this. We'll talk about temperature also when we do the thermochemistry section or the thermodynamics session in a couple of weeks. Temperature is the measure of the average kinetic energy of a sample. Kinetic energy is measured by, is used by this formula here. Kinetic energy is equal to 1/2 the mass times the velocity of the particle squared. And what this means, and what you should understand, is this. It is important, when I add these things to the question, it is important to know that particles at the same temperature have the same average kinetic energy. That means the particles have the same amount of energy as the other sample of particles. That doesn't necessarily mean that the particles are moving at the same velocity or speed, though. What you should understand about this is the following. Heavier particles move slower than lighter particles that are at the same temperature. Kind of a dumb example that I like to use is that if I were to run at a wall at 5 miles an hour, it'd probably break my nose. It would hurt, it wouldn't feel very good, but I'm moving at 5 miles an hour. If I had a giant freight train moving at 5 miles an hour at my wall, it would take out the wall. And why is that? Well, because the train is more massive, it has a lot more mass associated with it, it has a greater kinetic energy. In order for me to actually break through that wall, I'd have to be moving significantly faster. And this shows us that kinetic energy, mass and velocity are inversely related in terms of kinetic energy. So in general, heavy particles move slower than lighter particles at the same temperature. However, once again, temperature is the measure of the average kinetic energy. So if I have a sample of particles and a sample of particles at the same temperature, they have the same kinetic energy. So it's important for us to remember that kinetic energy and velocity are not the same thing, though they are related. And for your viewing pleasures, one other meme. I love the kinetic molecular theory for gases. This is just something that I would keep on the back of our minds for when we're talking about some of the properties of gases. I'm just going to go ahead and quickly kind of read through these and answer some of the questions that may come up from this. First off, gas particles are in constant, rapid, random motion. They're bouncing off of each other. They're bouncing off the walls. It's a crazy, chaotic world. Gas particles are infinitely small compared to the large distances between them. What this means is essentially if I were to have a particle here and a particle here, in reality, it would probably be like off the screen on Mars. It would be so far away compared to the other molecule that in reality, they probably should never collide. Gas particles are infinitely small compared to the large distances between them. 3, there are no forces of attraction or repulsion between gas particles. 4, all collisions between particles are elastic. Elastic means that there is no loss in energy when the collision occurs. And the last one is really just a restatement of the temperature definition. Temperature is directly related to the average kinetic energy of the particles. All right, here's what's fun about this list. Ideal gases follow all these things perfectly, and ideal gases do not exist. They are a theoretical thing that scientists study in order for us to understand some of the baseline properties of gases. So no, gas particles are not infinitely far apart from each other, but they're very far apart from each other. We literally just got finished talking about how particles are attracted to other particles. That's called intermolecular forces. So there absolutely is a force of attraction between gas particles. It's just that they have so much energy associated with each other that when one comes flying by another one, they're like, I feel the force of attraction, and then it doesn't because they're just flying right by each other. And there's no such thing, if any of you guys have taken physics, there's absolutely no such thing as an elastic collision on planet Earth. We come very close, but that is, not a true thing. What we should take away from this is that, first off, all of these conditions and statements allow for us to create the ideal gas law. And this statement right here, a real gas like carbon dioxide, oxygen, nitrogen, they are more ideal at higher temperatures and at lower pressures. The reason this is because at higher temperatures, you're able to overcome those forces of attraction significantly easier. And at lower pressures, you're causing the particles to have further or more distance between them. So yeah, Yana, basically, all these things here that I just listed are the properties of an ideal gas. And real gases can be modeled by these, but they have slightly different behaviors associated with them. Now time for the math. Ideal gas law. Probably most of you have this drilled into the back of your minds. PV equals nRT. Don't forget, it is technically on the formula sheet, and it's really straightforward to use. It's really just a plug and chug equation. So gases apply pressure by colliding with the walls of their container. We know that the units for pressure in this equation are going to be in atmosphere if you use the universal gas constant 0.0821, which is the one that's listed on your formula sheet. Volume refers to the size of the container. Remember, gases will always occupy the volume of their container. Moles refers to the amount of particles. The universal gas constant is R, is 0.0821 atmosphere liter per mole Kelvin. And we already talked about temperature. If you're going to be using this equation, use pressure in atmosphere, volume in liters, moles in moles, and temperature in Kelvin. Always keep that on the back of your mind. Those are the units you have to use when using this equation. There's one other variation on the ideal gas law that I think is actually kind of important to keep on the back of your mind. While you'll never probably use it, you'll maybe asked some qualitative questions about this. And this is PM equals DRT, and I so lovingly deem this as night dirt. You get it? Night dirt. PM is night, and then dirt. Night dirt. Okay. So really, it's just a manipulation of PV equals nRT. Okay. And what it does is it allows for us to relate density and molar mass with each other. But everything else in terms of this equation is the same. So pressure is in atmospheres. The R, the universal gas constant, will still be 0.0821, and temperature will still be measured in Kelvin. The density will have units that are in grams per liter, and the molar mass, as we know, is grams per mole. So I have two questions. I want you guys to, if you have a pen, paper, calculator, try these out, work them out. I'll give you a few minutes. What I'm going to do is actually kind of backtrack a second here. There was a really good question that I want to make sure is answered. So the question that Perla asked is, are H bonds bonds? And the answer is no. Hydrogen bonds are not bonds. And you're like, why? And the reason this is because they are a very strong force of attraction between particles. And so what you should understand or think about is that hydrogen bonds are intermolecular forces. So when I'm talking about the molecular solid called ice, the attractive force between one water molecule and another water molecule is called a hydrogen bond, which is not a bond, but an intermolecular force. And yeah, Mackenzie, of course you can use any manipulation on PM equals DRT by dividing the molar mass. You absolutely can. Mackenzie says, if you were writing out your work for PV equals nRT, will you get points off for taking, will you get points taken off your answer for not using labels in the equation? Are you referring to units? If you're saying units, the answer is absolutely not. You should only ever use units for your final answer. It is a huge waste of time to write your units. You should be considering units because they can kind of manipulate them or try to trip you up, but don't ever write units in the math. Just add or slap on the units at the end. The biggest question that I've seen them ask units for is for the rate constant for 0, first, or second order. And so making sure you kind of have those units there for those is really important. All right, cool. So hopefully you guys have kind of worked through the math. Shoka has the answer at 0.17 grams of sulfur hexafluoride, and I think that is what I got. Yeah, nice. So if you look through my work here, the first thing I did is I listed out all the values or variables given to me. I was given pressure is 1.12 atm. The volume, I immediately changed that to liters. The temperature, I immediately changed that to Kelvin. Put all the values in for PV equals nRT, and I solved for the moles of sulfur hexafluoride and got 0.0011. I multiplied that by the molar mass and found that it was 0.17 grams. One of the fun things about the AP test, they don't always do this, but sometimes they'll provide you with the molar mass of a substance, so you can just use that. You don't have to actually go and calculate it. Last but not least, it does have 2 significant figures, so I listed my answer with 2 sig figs. Remember, you're allowed for most of the test a variation of 1 sig fig. On the normal AP test, there is a question that is you have to answer with the correct number of significant figures. I don't know if they're going to use that one this year or not. There's a lot of things up in the air. And yeah, Perla, I think they probably would give molar mass because you could just look it up yourselves. But yeah, who knows? This is going to be a fun year. But you guys are killing it. You guys are doing a lot of really great work. All right, one last question. What is the density? So you see density and then a gas, given this pressure and temperature. So if you see this, you're like, night dirt. What is the density of xenon with this pressure and temperature? So basically, what we're going to do is make sure we have pressure and temperature and the units that we need them in. And we look up the molar mass for xenon. So by doing this, we end up using the equation, and it's actually a pretty quick question here. We end up finding that the density of this particular gas is 3.67 grams per liter. So interestingly enough, the pressure and temperature will affect a density of a gas, and you should keep that on the back of your mind in case a question does arise from that. Usually these are more qualitative questions, but you can still apply this concept of PM equals DRT to those qualitative questions. All right, last couple things, and then they're done for today. Dalton's law of partial pressure. This is a fun one. It's really just addition. So basically, if we were to have a mixture of gases, the sum of each individual partial pressure is going to equal the total pressure of the system. So pressure of a gas is independent of the pressure of the other gas that's in the same mixture. What I mean by this is that if you were to have a singular gas inside of a container, the pressure of that gas is the same if you were to add a different gas into that mixture. It's just that the total pressure of this system will increase. Partial pressure is the pressure of a gas in a mixture of gases. The pressure of one gas can be assumed to be independent of the pressure of the other gases. Dalton's law of partial pressure, which is represented mathematically above, states that the total pressure of a mixture of gases is the sum of the partial pressure of each individual gas in the mixture. This is a great qualitative little thing for us to understand, but basically the only time I've really seen this come up is in a situation where we collect gas over water. Now, there's a lot of variations on how we can actually do this. This is just one of the images I found where we have a chemical reaction that produces a gas. We can then bubble that gas into a flipped graduated cylinder, and then that gas collected above is the gas that we're interested in. So in the flipped graduated cylinder, the gas from the reaction bubbles to the top. It's trapped up top. Because water can escape into the gas phase, and it does so all the time, we also know that there's some water vapor, and the amount of water vapor that's present is dependent on the temperature of the water. The pressure of the sample above the water is due to two gases. The gas that I'm interested in, the gas collected from the chemical reaction, and the gas from the water vapor. So there's actually two gases up there. And when I measure the pressure of that gas sample, I'm measuring the pressure of both of those things. So once again, when we collect the gas over water, the pressure that's provided to us is the collected gas pressure. We know by looking up on either a data table or it being provided to us, the vapor pressure of water at a specific temperature. So all you have to do is subtract the collected pressure by the vapor pressure of water to find the pressure of the gas that we're interested in. So once again, when collecting a gas over water, and the language is really clear, they're always like, you're collecting a gas over water. And you're like, oh, got to subtract that one thing, but vapor pressure. Since water's vapor pressure is dependent on the temperature, the value is always provided to you. It's never not. So they will tell it to you. You don't have to memorize these things, and you're not supposed to be looking stuff up during the AP test anyway. So it'll be very clear in the test if this is something that you're expected to do. And that's actually it for me today in terms of material. There is obviously a lot more in this particular unit, in Unit 3. I think that this will probably be one of the bigger units tested on, but once again, they're only asking you 2 questions. Yeah, and so Anika, I think stream number 9, I'm going to do practice AP questions to help you out and kind of think about styles of writing, and basically the way I'm going to do it is post the question, write out the answer. Post the question, write out the answer. So yeah, following along would be obviously helpful with that. But yeah, you're all used to your own ways and methods of studying. I'm assuming most of you are juniors or seniors. You've hopefully figured out this studying thing at this point. I'm gonna stick around for 5 minutes and just kind of see what kind of questions you guys have. I'm gonna open it up to anything from Unit 1 till now, and just kind of see what you guys have. Yeah, yeah. My junior year was rough too. I remember that being a hard year. Not only though, like your guys' junior year must be brutal because you have to do all of this at home too. Trevor, I am so sorry. I know. And then so seniors this year, they don't have graduation, they don't have prom, grad night. That's rough, man. I feel you. I really feel you on that. All right, Mackenzie asked a really good question. Do you think the test will be more theory or calculations? And so once again, I'm starting to answer this question. Do you think tests will be more theory or calculations? And I think the answer to this is make it as similar or close to a AP test as possible. Meaning, what you guys should be doing is looking at former or past AP tests, which they provide for you online. You just have to Google like AP chemistry and then year. So AP chemistry 2019. And then work your way through those FRQs, answering everything that you can. And I always recommend to my students trying to answer them before looking up the answers. So write it out and then check your answers. Obviously, anything related to acids and bases. So if you see like a titration curve, if you see a Ka or Kb value, and the applications of thermodynamics, so that's going to be entropy or Gibbs free energy. Those things will not be on the AP test. Enthalpy still is, so delta H is still on the test, but anything related with the S or the G will not be. Nice, Yana. That's a good thing to be on the keep on the back of your mind. So I'll post this so everyone can see it. Yana went ahead and said that they recently put a bunch of FRQs on AP Central that will be the same layout as the test in May. So that will be an excellent resource for you guys and thing that you should be practicing and studying. Cool. Is there any? I know you guys are like AP test. Was there anything subject related that anybody has issues with? Anything that I can clarify in terms of the content before I head out? Cool. So with that being said, what I'll just do is this. Go over the stream again, go through the slides again if you need to. And next week at the beginning of our session, if you guys have any, like, I have to answer this question, feel free to ask it then. I'll make sure to put some time aside for that. So anything from Unit 1, 2, or the first half of 3, and we'll do it then. Okay, guys? You're doing awesome. Make sure to get your rest. Make sure you're getting sleep, eating good food, making sure, you know, you're all on the right mindset. So have a great day, guys. And I will see you all very soon. Bye, y'all.